Our work is on transfer learning of human preferences for proactively assisting users in assembly tasks. We focus on manual assembly tasks where humans must perform the intricate assembly operations, and robots can assist humans by doing the secondary work, like supplying tools and parts to the user. The goal of our research is to optimize the performance and fluency of the human-robot team in a single execution of the assembly tasks. This is because we consider assemblies like building a specific satellite, which will only be done once by a given user in the real world. In order to improve performance in such collaborative tasks, robots need to be able to predict the future actions of their human partners. For example, if the robot predicts that the next human action will require a screwdriver, the robot can proactively go to the storage and fetch the screwdriver to save time. However, a challenge in predicting user actions is that each user can perform the same assembly task in a different sequence depending on their individual preferences. And thus, robots need to learn the preferences of their human partner in order to proactively assist them by predicting their actions. Prior work in learning human preferences has largely relied on demonstrations provided by the user in the given task. However, in real-world assemblies, providing demonstrations can be very tedious and time-consuming. Moreover, it may not be beneficial to obtain demonstrations for an assembly task that will only be performed once by a given user. So, how can we optimize the team performance without any user demonstrations in the actual assembly task? In our prior work, when assembling an IKEA bookcase, users explained their preferences in terms of features like physical or mental effort that are task agnostic. For example, the user on the left preferred to perform all similar actions in a row to reduce their mental effort, whereas the user on the right preferred to assemble the bookcase vertically in order to reduce their physical effort. This has also been seen in prior work where users perform a physical task with the objective of minimizing their short-term effort, for example, avoid constantly changing the tool that they are using, or their long-term effort, for example, finishing all high-effort actions at the start of the assembly. And so, instead of learning from demonstrations in the actual assembly task, our key insight is that we can learn the task-agnostic preferences of a given user from a solitary demonstration in a much shorter canonical task where users can express their preferences and transfer them to an actual task where we want to predict user actions. We model each assembly task with a different Markov decision process, each having their own set of states, actions, and transitions, and consider that the reward function captures each user's preference and represents the objective that the user is trying to optimize. While the canonical and actual assembly tasks are represented by different MDPs with completely different states, since our features are task agnostic, we can have a feature function that maps states in both the tasks to a common feature space. With this, we can represent the user's reward function as a linear combination of the task agnostic features, where the feature weights are specific to a user's preference. Equipped with this formulation, our proposed system first learns the weights for a given user from their demonstrations in a canonical task using the maximum entropy inverse reinforcement learning approach. Then, based on our insight, we use the weights learned in the canonical task to compute the user's reward function in the actual task. And then, assuming that the user is trying to maximize the rewards, we can compute a policy and use it to predict user actions. To test our approach, we performed a preliminary study where users performed a canonical task with only 6 actions and an actual model airplane assembly with 17 actions. Here, we manually designed the canonical task such that it has actions that are diverse in the task-agnostic features, like having actions that lead to different physical and mental effort states. For the 19 users that performed both the tasks, we saw that the task-agnostic preferences transferred from a canonical task are useful for predicting user actions in a completely different actual task. Note that we did not tell the users that the two tasks are related, and we also counterbalance the orders of the task. While the results from our preliminary study were promising, we saw that some users may change their preference by the time they perform the actual task. Users may change how they weigh the task-agnostic features, or consider additional features in their objective that we did not model in the canonical task. Our proposed system handles the two scenarios in the following way. First, to account for changed user weights, our system only considers the transferred weights as a prior and uses them to predict user actions in the actual task. If at any step during the actual task, the user performs a different action than what the system predicted, we update the weights online based on the user actions that the system has observed so far. Then we use the updated weights to predict the user action at the next step. Next, to account for missing features, we assume a list of candidate features that the user may consider in the actual task. Thus, whenever our system makes an inaccurate prediction, we query the user with the list of the candidate features and ask them to select the feature that affects their preference. If the user selects a feature from the list, we augment it to the feature function that is used to compute the rewards and initialize it with a randomly sampled weight. Thus, our entire system not only transfers user preferences from a canonical task, but also updates them in the actual task online. We evaluate our proposed system in a human-robot assembly study with the same canonical and actual task as before. This time, we have the robot predict the next user action and proactively reach to the part required for that action. If the prediction is correct, the user can approve the delivery of that part. Thus, by proactively reaching to the part required for the next action, the robot can save the time that it needs to go from its start location to the location of that part. As a baseline, we consider a reactive robot that always fetches the correct part, but does so only after receiving a command from the user, and thus may require more time to supply the parts to the user. We see from this study that by proactively assisting the user using our proposed system, we can reduce the user idle time as compared to the reactive baseline. And this is also seen in the subjective responses provided by the users. This is because our system has an overall high accuracy of predicting user actions. We see from our ablations that our system of transferring and updating the preferences online outperforms transferring weights without online updates, and the baseline of performing online updates without using any transferred prior. Thus, the key takeaways from our work is that task-agnostic features can be used to capture user preferences across different assembly tasks, and user preferences learned in the canonical task can transfer to the actual task for predicting user actions. Lastly, both transferring preferences from the canonical task and updating the preference online are critical for improving performance and fluency in actual assembly tasks. With that, I can take any questions that you may have.